Okay. Okay, thank you very much for the introduction. First, maybe I have to be sorry to apologize that this is not about generalized hydrodynamics. And I'm also maybe sorry for this long title, but anyway, let me start. So first of all, I'd like to thank the organizers for giving me an opportunity to visit this very, very nice place with a nice beach. And I also would like to thank organizers for giving me an opportunity to give a talk here. So my talk is based on a collaboration with these people. And in fact, the results were already published here. So if you are interested, you can study more from the reference. Okay, maybe I start from very, very general remarks. So as I already mentioned a little bit, my talk is not about generalized hydrodynamics, not about basically quantum mechanics. My talk is about the fluctuations of classical systems, in particular stochastic processes, which represent some non-equilibrium many-body systems. In fact, maybe a lot of you don't know me. The reason is basically that I have mainly been working on such subjects, meaning classical stochastic non-equilibrium systems, in particular on the asymmetric simple exclusion process and the KPZ equation. Maybe you know some names, but not much. So I will explain these from the beginning today. But I have also interest in some quantum systems, in particular recently, and recently wrote a paper on large deviation of a spin current for XX model. And I was a little bit hesitating. Maybe I should talk about this because this may be of more direct interest to you. But I thought that this conference was, at least at the beginning, aiming to have more broader perspective about fluctuation, hydrodynamics and the fluctuations. So I decided to talk about the classical thing. Anyway, let me go on. So here is the plan of my talk. So so I think I have to explain some basics about classical stochastic systems. The first part is the kind of single component case, which is basically about the ASEP and KPZ equation. And I will explain the hydrodynamics and also fluctuations for these particular models. So this is related to single conserved field case. Then I'd like to explain about the multi-component system case. And this is related to nonlinear fluctuating hydrodynamics. So this is about the hydrodynamics with nonlinearity, but we also want to study the fluctuations, right? Mainly for classical systems, but it could be also applied to quantum systems as well. So this is a still conjectural theory about the fluctuations for multi-component systems. And even though my talk is basically about stochastic dynamics, so this theory, conjectural theory, nonlinear fluctuating hydrodynamics, can be also formulated and applied to Hamiltonian deterministic dynamics. And then this third part is the kind of main contents of my talk. So this is about exact analysis to confirm a prediction from this theory to the case of simple two-species ASEP exclusion process, which has stochastic dynamics, right? So this is the plan of my talk, okay? Okay, so let's start from the single component case, ASEP and KPZ. So how many people don't know, haven't heard about ASEP? Okay, so there are still some. Okay, let's really start from the beginning. So this is an abbreviation of asymmetric simple exclusion process. So if you take the first letters, then ASEP. So this is ASEP. So this, well, one can define on a general dimension, but we will mainly focus on the one-dimensional case. So we consider one-dimensional lattice, and we consider diffusions of many particles. And each site is either occupied by a particle or is empty, like this. And each particle tries to do asymmetric random walk in continuous time in the standard setting with rate p to the right and with rate q to the left. So this means that if you consider infinitesimal time duration dt, this particle tries to hop to the right with probability p dt and to the left with probability q dt, right? So this is the meaning of the rate. And each particle tries to do this asymmetric random walk, but there are exclusion interactions among them. So if two particles are on neighboring sites like this left particle cannot hop to the right, this right particle cannot hop to the left. Right? So this is exclusion, and that's it. So this is the ASEP, very, very simple. But this already contains high non-trivial, non-linear effects, and this also has a fluctuation. So this is a kind of minimal model to study non-equilibrium behaviors of statistical many-body systems. Yeah, so this is a many-particle stochastic process, in particular Markov process. So this is a standard, one of the standard models in non-equilibrium statistical mechanics. One can formulate the time evolution of this process by using the master equation, which can be written in this way. So this is about the time evolution of a probability that the system is in some configuration, like this. And then this evolves according to this linear equation. And L star is the time evolution generator of this Markov process. And then by using this, for example, one can show that what is the stationary measure for this process. In fact, the so-called Bernoulli measure, in which all sites are independent and each site is occupied by a particle with probability P, or is empty with probability 1 minus P, 1 minus rho, sorry. So then the system is in a stationary state. So if you apply this state to this, if you apply this generator to this state, then this is 0, right? Okay, then you may wonder what is this generator. And for this particular case of ASEP, in fact, it is kind of well known for some people that this ASEP, the generator of ASEP, is very much related to the Hamiltonian of XXZ spin chain. I believe that this XXZ is much more familiar to you. Right, so let me explain a bit more concretely. So the generator for the ASEP, L star, can be written in this way. So I hope you understand this notation JJ plus 1. So in principle, this is a very, very huge matrix, but this JJ plus 1 means that this matrix acts on the space of sites related to sites JJ plus 1 non-trivially, and to the spaces of other sites, this acts as an identity matrix, right? And so this P corresponds to the hopping to the right, this Q corresponds to the hopping to the left. So this is the generator for ASEP. On the other hand, this is the famous XXZ spin chain Hamiltonian. And then if you define capital Q to be the square root of ratio of P and Q, hopping rates, and then define delta, an isotropy parameter, in this way. And if you define some diagonal matrix V using this, where Nj is basically sigma j z, then these two big matrices are related by the similarity transformation in this way. I put this modular boundary condition. There's a little bit tricky point of the correspondence. For example, periodic ASEP does not really correspond to periodic XXZ. So there's a little bit tricky, non-trivial point, but I don't go into the details for this. Doesn't mean, sometimes non-Hermitian matter, as you see, so this is non-Hermitian, but sometimes one can similarity transform to Hermitian matrix by similarity transformation. This is fine. Okay. Right, sorry. So then, so this is the kind of connection to the quantum integral systems. Yeah, so in a sense, ASEP can be also thought of as an example of quantum integral system from algebraic point of view, but ASEP and XXZ have, of course, a very, very different context. So for example, calculating averages of spin over particles, so they have completely different meanings. So we need rather different techniques to study each of them. Anyway, at the level of the generator, they are very, very related. And for the ASEP, the quantities we are interested in, for example, the current, integrated current, meaning we count the number of particles which hop from the side 0 to 1, for example, between time 0 and t. So this is the integrated current. And of course, we are also interested in correlations. Yeah, space-time or space-space, different points. Yeah, various correlations. Okay. Then, so this ASEP is still a microscopic model. It has microscopic degrees of freedom, and the dynamics is stochastic. One can consider, for example, hydrodynamics. And this has been established by basically probabilists, mathematicians, that the hydrodynamic behavior of this ASEP for the average density is described by this equation known as the Borg's equation. So this is nonlinear. This has nonlinear effects. So this is the hydrodynamic. So hydrodynamic behavior of ASEP can be studied by using this Borg's equation. This has been established mathematically. Right? U is, sorry, so macroscopic hydrodynamic version of the average density of particle. And naively, one can kind of derive this equation by writing down a time evolution equation for the average density from microscopic dynamics of ASEP. So for example, from the definition of the process, one can write down the evolution equation for this one-point function. Then from the rule, you see, so Nj is the occupation number at site j. So this takes only 0, 1. So this becomes 1 only when j minus 1 is empty and, is occupied and j is empty, or j plus 1 is occupied and j is empty, right? So these are the two contributions with p and q. And there's also kind of escape from the situation j is occupied with rate p and q. So this is the time of evolution equation. But unfortunately, we cannot really solve this because this is a one-point function, and in the time of evolution equation contains two-point function. So this is a very, very typical, usual situation, also in quantum mechanics, I think. But maybe naively, one can try to see what happens if we ignore the correlations. Namely, what happens if we replace this bracket of AB by simply product of two brackets, A average of A times average of B. Then you can write down some equation, nonlinear equation for the one-point function, approximated one. And then one can introduce lattice constant, maybe denoted by A, and take expansion with respect to A. Then when A goes to 0, then what we get is this Borg's equation. So in this way, naively, one can get this hydrodynamic equation from microscopic description of ASEP, right? That's right, yeah. Yes. Yeah. Yeah. Well, yeah, so this is just a physical. I wanted to just explain in which kind of argument one can see this, but this was established by real mathematicians. Yeah. No, of course not. No. Right, so by using this Borg's equation, one can predict various macroscopic or hydrodynamic behaviors. For example, the current for the uniform density case with density rho is simply given by P minus Q rho times 1 minus rho. Because if you write this as a continuity equation, this part times this part is corresponds to the current. So for the uniform density rho, you get this one, right? Okay. Then, but we are also interested in fluctuation and correlations, right? In the case of ASEP, in particular, for the special case of TASEP, in which particles hop only in one direction, so when P is equal to 1 and Q is equal to 0 case, then one can study fluctuation, what is also based on microscopic model calculations. So the simplest case is to start from this initial condition, step initial condition. So this is a kind of special case of partitioning protocol, right? But in our community, we still call this basically step initial condition, but they are basically the same. And we know how to describe the macroscopic behavior, hydrodynamic behavior. And in this, if we start from the step initial condition, the average density profile is the Layer function form, like this. So this is just simply linear, right? Then you can, especially around the origin, so the density is always 1/2. And in the long time limit, we expect that the situation becomes basically stationary around the origin with density 1/2. So at the origin, we expect that the average current is basically 1/4, right? If you calculate from this, so we are now considering ASEP, in which P is 1 and Q is 0. So this is 1. And we consider the case in which rho is 1/2. So you get J equal 1/4, right? So this is the average current around the origin for ASEP for this particular initial condition. But we are interested in fluctuations around that macroscopic value. And in fact, it turns out that the fluctuation scales like t to the 1/3, not 1/2, which is typical for Gaussian. So there's something non-trivial going on in this. So this is in fact related to the KPZ universality class. And anyway, so this is kind of well-known fluctuation scale. And we are more interested in distribution itself for the scaled current, which appears here. And in fact, for the case of ASEP, with this step initial condition, the limit, yes? The P is just a rate, not a probability. So with probability for during infinitesimal time duration dt, if you consider discrete time, then if P is the probability of the hopping to the right, then this becomes deterministic. But we are considering continuous time for the moment. Right. So now we consider the current, integrated current as the origin, right? And as I said, macroscopically, this would behave like T/4, and we subtract it, and the scale is expected to be T to the 1/3, and we put some coefficient. Then, so this is a scaled version of the integrated current as the origin for this particular initial condition. And then we consider the large T limit of the probability cumulative distribution function of this scaled integrated current. And then he could show that in this limit, this goes to some non-trivial distribution function denoted by F2 of S. And this turned out to be the so-called GUE trace rhythm distribution, which can be defined in this way as a Fredholm determinant with the Airy kernel given by this. And one can check that simulations and this theoretical curve matches very well. Right, so I don't know. So maybe some of you are not so familiar. Yes? Sorry? Wave breaking? I'm not sure. Well, at least for this case, this does not happen. So the macroscopic behavior is just a linear slope, the Layer function fun. So there's no such difficult. No. So this continues simply in this case. Yeah, maybe we can discuss later. And maybe you are not so familiar with trace rhythm distributions or random matrix. So this GUE trace rhythm distribution appeared in a completely different context of random matrix. So let's consider n-dimensional Hermitian matrix H, and we consider some probability distribution for this matrix H, and the measure is given by this. So H, we take trace of H squared, we put it on the shoulder of the exponential. So then this gives you some measure for a Hermitian matrix. So this is GUE, Gaussian unitary ensemble. And then we also have kind of probabilities for eigenvalues denoted by xi's. And remarkably, for Gaussian ensembles, one can write down explicitly the joint distribution, joint density functions for the eigenvalues, which is given by here. So you see some free Fermionic feature for the eigenvalues of GUE. Then by using this, it is rather easy to study the largest eigenvalue distribution as the n-fold integral of this density. And then if you take large n limit, n is the matrix dimension, then what you get in appropriate limit is the GUE trace width distribution. So this is the original context in which the GUE trace width distribution appeared. But as I said that the same distribution function appears in a completely different context of this stochastic process, tacit, right? So there's strong universality behavior behind the scene. Okay. Then, so this was about the fluctuation of current. But what about the correlation? And can be also studied, especially for the case of ASEP. These were studied by these people in the early 2000s. First for the so-called PNG model, and then also for ASEP. And in the stationary situation with density rho or 1/2, they could study stationary two-point correlation function. And then, yeah, I cannot give you the explicit formula because it's pretty complicated. But anyway, there's some explicit formula for the two-point function. And by using the formula, one can draw a plot of the two-point function denoted by G or G2 double prime. And it looks like this, right? Anyway, so this can be studied analytically as well. So this was established by doing microscopic calculations, as I said. But maybe one can try to obtain similar results by putting noise effect to the hydrodynamics, right? So I already showed you the Burger's equation, but let's modify a little bit the coefficients and variable, and we also put the diffusion term. So this corresponds to the so-called viscous case. Sorry, maybe I should show you again. Originally, the Burger's equation is like this. So maybe by setting u minus 1/2 to u, this becomes u squared, and then maybe this can be replaced by 1 or so. And yeah, we could also put diffusion term. They are, of course, somewhat different, but here I want to say that they are basically the same thing. Then up to here is the Burger's equation with the diffusion term, right? Then we can, so there's no fluctuation at this point. This is just a nonlinear partial differential equation without any fluctuation. But we want to study fluctuation, right? Maybe we can try to put noise by hand. Because we want to have a conservation rule, so we put also this ddx, meaning that we consider noise to the current, not to the density, right? Anyway, so this is the Burger's equation with the diffusion term and also noise added. And here, eta is taken to be Gaussian noise in a standard way with mean 0 and the covariance given by a delta function. So this is the so-called noisy Burger's equation. So we can expect that this noisy Burger's equation describes also fluctuation and the correlations of the microscopic model like ASEP. But we don't know because at this point we put this by hand, right? But we can hope that they have the same universal behaviors. And in fact, we can also introduce a variable h to be the integral of this variable u. Then the equation can be written in this way. And this is, in fact, the KPZ equation. In the language of exclusion, yes? Yeah, of course, in the KPZ, of course, one can put arbitrary parameters, but they can be taken out by some rescaling. So they're not so important in this discussion. Yeah, maybe again later. So in the language of exclusion, sorry, yes, yeah. A diffusion term, well, okay. So at the Euler scale, this is the equation, but for example, in this calculation, if you take up to first order in A, then we have this diffusion term. And in fact, there is slightly different scaling of the ASEP, in which we also get this diffusive term. So in many ways, there's also slightly different version in which we have diffusion term. And yeah, if you for example, if you want to find a solution for this equation is not really enough. So from here, you get some unphysical solution. But to get the real solution, physical one, then first, one way is to first put this diffusion term, and then solve it. This can be done. And then you try to take this A goes zero limit. In this way, they are all connected. All right. Yeah, in the language of exclusion particle model, so the mapping is very simple. So this is the configuration for ASEP. If you replace this empty site by this upward slope, occupied site by downward slope, then particle configuration becomes surface configuration, and dynamics of ASEP corresponds to some surface growth model. And in this mapping, the current fluctuation for ASEP we are interested in is nothing but the height fluctuation of this surface growth model. And for example, the step initial condition, which we are studying for ASEP, corresponds to the wedge type initial condition for the surface growth case. Right? Anyway, so let's come back to the KPZ equation. So this is the equation I wrote down in a previous, right? That's really the same one. So this is, and here h of xt has the meaning of height at position x and at time t. And KPZ means here the Kada Parijsan. Maybe in this community, I'm not sure. Some of you think that the KPZ should be this one, but this is in our community, so KPZ is more like this one. Anyway, so for this equation, one can also consider fluctuation of the height. And then we expect, so there's some average behavior, and we expect that the fluctuation is like t to the 1/3, and then the non-trivial distribution should be contained in this random variable. We are expecting this shows universal behavior called the KPZ universality class. And in fact, for the KPZ equation itself, so GUE trace rhythm distribution was established for the wedge case almost 10 years ago. And the stationary two-point function for the KPZ equation was also studied by us. And then they show the same universal functions, GUE trace rhythm distribution and the two-point function, right? So in this way, we can think that by adding noise to the hydrodynamic equation coming from the ASEP, one can in fact study universal fluctuations of a microscopic model. In fact, for the case of the KPZ equation, the situation is even better in the sense that if we take appropriate weakly asymmetric limit, then in fact one can derive the KPZ equation itself from microscopic dynamics of ASEP rigorously. Anyway, and there's also, in mathematics, there's another issue of well-definedness of the equation and so on. This led to the Fields medal for Martin Heider. But this is not very important in our discussions today. Sorry. So this is the short summary of the first part. So ASEP is a microscopic model with stochastic dynamics, which many of you may not like so much. And this has a single conserved quantity, so the easiest case. And hydrodynamics is well known to be given by the Borget equation. And we're interested in fluctuations and correlations. They can be studied microscopically, and they have been studied. And we could also see that if we add noise to the hydrodynamic equation, the Borget equation, then we get the KPZ equation. And this can be also studied, and it shows the same universal behaviors as for ASEP. This is the situation for single component case, right? Obvious question here is that what about multi-component case? So this is related to my main topic today. But there's another interesting context related to multi-component case. Let me explain a little bit. So this is about nonlinear fluctuating hydrodynamics. So forget about ASEP for a while, and let's consider one-dimensional Hamiltonian dynamics given by the Hamiltonian given this way. And the potential is given here with cubic term and the the fourth order term. So this has some nonlinearity. And of course, this is non-integrable. It's very, very difficult to study. And in fact, these people, this is called Fermi-Pasta-Ulam chain. And they try to see thermalization at the beginning in the original paper, numerically, but somehow recurrence seemed to occur. But this created a huge interest in this kind of nonlinear problem. And this has led to various notions like chaos, soliton, and so on. Anyway, so this is a non-integrable case. So we have three conserved quantities, basically density, momentum, energy, but technically it is more appropriate to consider so-called stretch, which is defined to be difference of two particle positions. Of course, maybe many of you in this audience are more interested in integrable case. So if we take, for example, exponential potential rather than this nonlinear FPU potential, then of course there are infinite number of particles. So then the story becomes different. But today, here, we stick to this non-integrable case with 3 conserved quantities. From physical point of view, this kind of problem also has motivations because they show very, very interesting anomalous heat transport and so on. And because although this has been introduced long time ago, this is still difficult. It is still difficult to study, in particular, long-time behaviors. But rather recently, it has been kind of expected that maybe some aspects of the long-time behaviors of such systems may be understood by using a connection to KPZ, which you learned in the previous slides. So microscopically, we can simply try to rewrite the evolution equation, Newton equation, Hamiltonian equation, in the form of continuity equation. So this is the stretch difference of xj's and momentum and energy, as usual. Then the time of evolution equation is written in this way, which can be summarized as the continuity equation in this way. So this is very, very standard. So this is just a rewriting of the microscopic equation. But maybe now we can consider hydrodynamic behavior, as in the case of ASEP. ASEP is microscopic model. We can consider hydrodynamics. This was the Burger's equation. In a similar way, we are now considering microscopic Hamiltonian dynamics, FPU chain. We want to consider hydrodynamics. And of course, this should be written in this way of continuity equation. Now, by simple chain rule, one can rewrite this equation in this way, where A is a 3×3 matrix, which is defined this way. And suppose the situation in which situations are basically constant. In this case, A is also constant matrix. And then we can try to diagonalize this 3×3 matrix. And then the eigenvalues are denoted by C1, 0, -1. And then correspondingly, we can kind of switch to this diagonalized mode from original G to phi. Then for each mode, the equation here is simply written in this way. So this is simply propagating with speed C alpha, right? So at this Euler scale, each mode just propagates ballistically with speed C alpha. This is the hydrodynamic, it's very, very simple hydrodynamic description. But as in the previous case, we're interested in fluctuations. In fact, in simulation, if you do it, even though we also see these ballistic behaviors, there's also some broadenings of the peaks, which is related to fluctuations. And we are interested in describing such fluctuations. And as before, maybe we can try to study such fluctuation effects by putting noise to the hydrodynamic equation by hand, right? Then, in this case, because of the fluctuation dissipation theorem, we should also add this diffusion term, as before. Then the equation looks like this. Then if we consider a situation in which the density and so on are almost constant, then we try to expand these variables around this equilibrium situation. And if we take up to first order, then the equation is linear, but this is not enough to describe these broadening fluctuations. So then we try to take up to second order, like this. Then this becomes now the nonlinear equation. And then again, as before, for the hydrodynamic equation, we switch to the normal mode by diagonalizing the matrix A. Then in this normal mode, the equation now looks like this. So this part is basically the same as before, propagating ballistically. But now we have also this nonlinear term, and also we also add noise, and also noise term. So this is the so-called nonlinear fluctuating hydrodynamic equation. So this is nonlinear equation, and also fluctuation effect is included as noise here, right? Yes? Yes? That's true, yes. Mm-hmm. sure. The normalization of which one? Yes. Okay. Yeah. To take this R, yeah, one has to take appropriate R to satisfy normalization condition. Yes. Yes. Yeah. How? In such a way that this should be compatible with the KPZ equation, basically, for us. No? Sorry, maybe we can discuss later. Sorry. Anyway. And so this matrix, this G is a matrix. So this has some correlations between normal modes. But in the hydrodynamic scale, so this had a kind of definite speed. Each mode has definite speed. So naively, we may expect that basically in the long T limit, correlations are not so important. So we can simply try to take diagonal part of this matrix. Then each mode becomes independent. Then this equation is really the Burgers equation, noisy Burgers equation for the single component case. Right? So this is very, very naive, but in this way, one can kind of expect that the long-time behavior of each mode in the Hamiltonian dynamics may be described by the single component KPZ equation. Even though this is very heuristic, especially we put the noise by hand, right? So there's no reason to believe it. But prediction is rather concrete, so we can try to check in simulations, for example. And if you do that for some nonlinear potentials, for example, a very simple one like this, then one can see rather good agreements with the prediction from the nonlinear fluctuating hydrodynamics. In fact, this is the correlation, 2-point correlation for the so-called sound mode. So there's a plot and also theoretical curve. Now, theoretical curve is really the same thing as in this one. So this was a universal 2-point function calculated from ASEP, single component model. And the same curve is plotted here. And this is almost the same as the numerical simulation for nonlinear, for Hamiltonian dynamics with this nonlinear potential. So the conjecture seems to be pretty well, right? Of course, for theoretical physicists, the challenge is to prove this, for example. But this will be quite difficult because what we want to study is Hamiltonian dynamics, which is not integrable. How can you do that? It's difficult, right? But of course, but still, I think this is a very, very important question, conjecture, for theoretical physicists. Okay, sorry, yeah. So this was for the original conjecture. Conjecture was for 2-point function, equilibrium 2-point function. But if you remember the story for the ASEP, we also studied current fluctuations and so on, which shows Tracy-Widom type distributions. And one could also consider similar situations for Hamiltonian dynamics. Then, yeah, they also studied such fluctuations for the currents for this Hamiltonian dynamics, and they could observe also GUE Tracy-Widom distribution. So this is also a conjecture which we want to prove theoretically, but it's difficult. Okay, so this is a short summary of the second part about nonlinear fluctuating hydrodynamics. So we are considering non-integrable one-dimensional Hamiltonian systems, which should have 3 conserved quantities. And hydrodynamics can be basically written down, and this can be diagonalized to 3 ballistically propagating normal modes. So this is the situation for this case. And we are interested in fluctuations. Maybe we could try to study such effects by putting noise by hand. So this is the nonlinear fluctuating hydrodynamics. And each mode seems to be basically given by the KPZ equation. So then we can get very concrete conjecture that each mode, correlation of each mode may be described by the one for the KPZ, single component KPZ equation. And simulations show good agreement. Proving this conjecture maybe seems very difficult, but maybe it could be easier for stochastic dynamics with more than one conserved quantity. So this is what we want to do for the two-species exclusion process. Well, the two-species exclusion process, right? Are there other questions for second part? Yes? It's possible, but yeah, it's certainly possible. But there have not been so many works. For the moment, people just put the usual Gaussian noise and they compare with simulations. They show reasonably good agreement. And I don't know, maybe in some special cases, one should take other types of noise, but I don't know. Other questions? No. All right, so let's go on. So now in this way, we wanted to find some concrete model with more than one conserved quantity in which one could really prove the conjecture from microscopic dynamics, right? And as an example, what we took is this two-species exclusion process, which was introduced a long time ago by these three people, Amdt-Heinzel Rittenberg. So we call this AHR model. So this is a two-species version of basically ASEP. We have now two species of particles, plus and minus particles. Plus is black dots, minus is white dots. So plus particles are basically ASEP, which hops only to the right with rate beta. And minus particles are also like ASEP, which hops only to the left with rate alpha. But there are exchanges. When plus particles and minus particles are on neighboring sides in this order, then in this case, they swap their positions with rate 1. So this is the AHR model we consider in the following. And in fact, this is known to be integrable, as shown by Cantini, like 10 by Cantini, like 10 years ago. In fact, we could also generalize this model in which the reverse hopping is also occurring with rate Q. And in this case, the stationary measure can be constructed by matrix product, but somehow integrability has not been shown. So if you are good at finding R matrix for a given model, maybe you can try for this as well. Okay, and for the moment, the case we could do analytic calculation has been restricted to the very special case in which this reverse exchange is not allowed. And also, we have to put some condition on alpha and beta hopping rates. So this should be satisfying that alpha plus beta equal 1. So this is a very special case in which we have factorized the stationary measure, right? So each side, all sides are independent case. So integrability is shown for more general case with general alpha beta, but yeah, for our analysis in the following, we stick to this case. So we could formulate the same nonlinear fluctuating hydrodynamics conjecture for this two-species stochastic process. And then there's a concrete conjecture, and for example, for the two-point function. And this, from Monte Carlo simulations, we could check this. So they are also agreeing very well with the prediction some time ago, several years back. And these people, Mendel and Spohn, they could also see the GUE trace evidence distribution if they start from step-type initial condition. Then now the question is, can we prove these conjectures for this exclusion type stochastic model with two conserved quantities? Yes, 5 minutes? Oh, okay. Yes. And then technically, from the technical point of view, the simplest situation, initial condition, which may be tractable, looked like this case. So we studied this case. So in this case, we consider, of course, infinite lattice. On the left, so this is like step initial condition again. On the left side, we have only plus particles with a density rho. And on the right side, we have only minus particles with a density 1. So they are all occupied. So in this case, so we start from this particular initial condition, and then we allow them to evolve according to their dynamics. Then there are some exchange and so on. And this is the time trajectory for a while. And for this particular model, we can also formulate the hydrodynamics. So this is a kind of replacement of the Burger's equation for the single component ASEP case. Now one can write down the hydrodynamic equation for two species ASEP. So this is given by this continuity equation with currents given by these expressions. So this is a kind of two component Burger's equation, right? Yeah. And again, one can do this diagonalization of the matrix A and switch to the normal modes. And for example, one can study several hydrodynamic behaviors. For example, the currents at the origin can be calculated explicitly, and they are given by these expressions, depending on rho. Okay, now the predictions from the nonlinear fluctuating hydrodynamics can be formulated in this way. So this infinite means that we are considering the case in which initially we have infinite number of particles, plus particles and minus particles. And anyway, so the conjecture is that for this particular initial condition with infinite number of plus and minus particles, if we take appropriate variable for normal modes, then the distribution should go to GUV trace rhythm distribution again. And somehow in this case, for another normal mode, we expect to see the Gaussian behavior. So these are the conjectures. And scaled variable for the normal modes look pretty complicated, but they are given by this. But they are not so difficult because these coefficients, as n and m, are the number of plus and minus particles which pass at the origin up to time t. So these are the random variables. And these coefficients come from this switching to the normal mode. And then this corresponds to the average behavior of the current. And then so for this mode, we expect to see the KPZ behavior, t to the 1/3. For this mode, we expect to see the Gaussian behavior, so we put t to the 1/2. And these coefficients are to see the nice limiting distributions, right? And we generalized a little bit these conjectures to the joint form that if we look at this joint distribution, then this should be given by a product of two distributions, GUE trace rhythm distribution and Gaussian. So this is basically the conjecture from nonlinear fluctuating hydrodynamics for our particular case. Right. So well, technically, so how can we try to study this analytically? As I said, this AHR model is an integrable system, so we can try to use standard techniques like beta ansatz and so on. In fact, one can apply the beta ansatz to this. And then by using that, one can write down the so-called Green's function, starting from the initial positions xi naught, yj naught, and at time t, they should come at positions xi and yj, right? And we suppose that initially, plus particles are on the left side, minus particles on the right side. So this is the condition for the initial condition. And then for the final position, the simplest case is this case. If the order does not change, the formula for the Green's function is rather simple, and it is given by this. If you see, basically, Zj corresponds to basically plus particle, and Wk corresponds to minus particles. And in this particular case, they are almost basically separated, independent. And lambda here are given by this. But so then there is no interaction of particles, right? Then the kind of next simplest case is that all plus and minus particles exchange their positions completely at the initial position. So this means that x and y should satisfy this. In this particular case, the Green's function has also a pretty simple form given by this. So this part is plus particle only. This particle is minus particle only, very similar to the previous case. But now we have some correlation effect as a product of whole k and j of zj plus wk. So this part includes some correlation effects, so plus and minus particles. But anyway, in this way, by using the beta ansatz, one can write down the Green's function explicitly. And then one can do kind of standard calculations as for the single component case, which I cannot explain here in this 1 hour talk. But anyway, by using that, that formula for the Green's function, one could write down joint probability distribution for the probability that current of plus particle is n. We start from the fixed number of particle case. Plus particles, there are only n particles. There are also m minus particle case. Now we have finite number of particle case. And then all particles pass the origin up to time t. So this is the joint probability of such event. And from the Green's function, one can do some calculations to arrive at this expression for this joint distribution function. Well, if you are not familiar with this type of calculation, this may look pretty complicated. But if you look rather carefully, it's not so complicated, right? For the Z integral, this has this structure, like the usual free fermions or van der Waals type thing. For W, it's the same. Then comes this correlation effect. And then, so original conjecture was for infinite system, but now we have formula only for finite number of particles. So we had to generalize a little bit the conjecture for this particular setting, and we could find that formulate a generalized conjecture for this finite number of cases, in which we expect that this joint probability for this event should be given by the product of these two distributions. This may look very, very similar to the original one, but in fact, the interpretation is rather different, but I cannot go into the details. From simulations, this generalized conjecture seems to be well-fitting, but we wanted to show it more analytically. And then starting from the multiple integral formula for the joint distribution function. So this part took some time, but at some point we noticed that maybe we should take the pole contribution at first from this point. Then we could rewrite the joint distribution in this way, where I1 is given by this only W multiple integral, and J is given by this Z multiple integral, and I2 is basically W integral, but this correlation effect comes here. And then in the large T limit, in this expression, we see that in fact, this is only around 1. So in this formula, it is seen that we can replace all ZJs by 1, simply by 1, in the long T limit. Then this becomes also only W multiple integral. Then we can basically apply the kind of usual techniques of random matrix calculations to do asymptotics. Then we could see that I1 and I2, these multiple integrals, behave like GU iteration distribution for this normal mode. And J behaves like Gaussian distribution, -1. And if you plug these asymptotics in this expression, then you could confirm this conjecture, generalized conjecture, right? In this way, we could give a kind of first microscopic confirmation of the prediction of the nonlinear fluctuating hydrodynamics, even though this is stochastic, right? Right, so yeah, so I should stop here. So to summarize, first there is a nonlinear fluctuating hydrodynamics, which gives very interesting conjecture about multi-component system, including Hamiltonian ones, and this is related to KPZ. And the original conjecture was for Hamiltonian, but proving it seems very difficult. I think this is still very important, but it's still very difficult at this point. But the same conjecture can be formulated also for stochastic dynamics, which should be easier. And in fact, we took particular model, named the AHR model, and we could in fact formulate a slightly generalized conjecture, and we could prove it analytically from microscopic calculations for this particular case. There should be many generalizations, various initial conditions, other models, and so on. Yeah, that's all. Thank you for your attention.
Questions?
So, introduction, you said this could perhaps be applied to the quantum case. Could you elaborate?